Okay, let's start our first lecture for today. It's nice to see such a lot of people after Friday evening in Moscow. The topic for today's lecture is Markov chain Monte Carlo, or MCMC for short. This is the alternative engine for solving Bayes inference problem, the alternative to the variational inference method that you have used almost in all lectures in previous day during the school. And just as a small recap of what we do in variational inference method, suppose for concreteness that we have some, well, simple probabilistic model, that we have some prior on our parameter theta and some likelihood function, which is decomposed into separate training objects. And what we're always interested in Bayesian inference is to deduce somehow the posterior probability on our parameter theta given our training data X, and in most of the practical cases, we are not able to calculate analytically the posterior distribution, and there's a need for some approximation to this posterior distribution. And if we say about variational inference methods, we usually introduce some, well, parametric family of probabilistic distributions and try to find the best approximate within our chosen parametric family, minimizing some discrepancy measure between the true posterior distribution and our parametric family. In case, if we consider variational inference, usually people take a KL divergence as this discrepancy measure, and minimizing this KL divergence is actually equal to maximizing what is called evidence lower bound, and we maximize this evidence lower bound with respect to our parameter lambda, parameter of our variational proxy. In a similar way, we could add some additional parameters to our joint probabilistic model, say a hyperparameter into prior or into likelihood, and if we want to tune this parameter during training, we could easily just add this parameter into our evidence lower bound and maximize it with respect to both lambda, the parameter of our variational proxy, and the hyperparameter that we want to learn from our data. This is the method that we have used a lot of times in previous days. But the main problem with this method that our variational proxy, our variational parametric family, could be quite poor approximate for the true posterior distribution, especially in the case when we deal with really complex probabilistic models like probabilistic models with neural networks. Our, well, say, fully decomposable normal distribution could be quite poor approximate for the true posterior. It couldn't be the problem if we are interested in just learning some hyperparameter of the model. If we are only interested in finding not this lambda, but this additional parameter that we maximize L with respect to this, we could say that it is enough for us that our alpha, which is a lower bound, if it has the same stationary point as the true likelihood function with respect to this parameter. It would be okay for us to learn this parameter. However, there are many cases, many practical cases, when we indeed need some good approximation for the posterior distribution. I would just give you one example, which is a very known one from statistical physics, known the Ising model. By the way, how many of you know about Ising model? Raise your hand. So, not quite many. So this is the very standard model which was introduced in the first part of the 20th century. It is the model from statistical physics that tried to describe the magnetic properties of a solid when we increase our temperature. If you take a magnet and start to heat it to increase the temperature, you would observe that there is a critical temperature, and in a short interval of temperature, your magnet lose all the magnetic properties. It is called the phase transition effect, similar like water transforms to steam when you heat it at 100 degrees. And so this is the model that tries to explain on why this occurs. Since this is a solid, it has some atomic lattice. For simplicity, let's assume that this lattice is two-dimensional. And in this model, we consider the individual magnetic moments of each atom, or sometimes it is called spin. And the spin can be either +1 or -1. And then our model is in model, introduce the energy of the altered configuration of spins within the model using this formula. And as you see, if your solid is a ferromagnetic, this energy would be lower if all the neighboring, or most of the neighboring atoms would have the similar magnetic moments. If they have the similar magnetic moments, our solid would have the magnetic property. So our energy would be lower if the neighboring magnetic moments would be the same. And also there is a term about the outer magnetic field, that if we have also additional outer magnetic field, it also influences our magnetic moments. Then this is the model from statistical physics. It means that we can't, with this model, say the particular configuration that we have in our solid. We can only introduce some probabilistic distribution on all possible configuration of spins there. And this distribution is usually introduced as a Boltzmann distribution. So as you see, this is proportional to exponent of minus energy. So the lower the energy, the more probable that this configuration is actually occur in our solid. And also here the temperature that stays here. And that is what we are interested in, to understand how our solid, how its magnetic properties behave when we change the temperature in the model. And here also state the normalizing constant Z that requires the summation over all possible configuration in the model. Okay, again, this is our model, and we are interested in measuring, well, several statistics. The most interesting one is the mean magnetization. So if we introduce the magnetization, the mean spin of the configuration of our model, it means that if most of the spin has the same sign, either +1 or -1, this mu would be close to either +1 or -1. And if we consider the mu squared and average it over our probability distribution, P of x, we would obtain the typical magnetic value of our solid for particular temperature. And if our model is correct, if it is correctly models the magnetic effects within the lattice, we should observe that if we increase the temperature, at some point this magnetization should drastically drops down. And also we are interested in some other statistics like mean energy variance, trying to understand at what temperature this energy is stable and which they are not. By the way, the important thing to note here is that this setting, I mean the estimation of these three statistics, is actually very similar to the Bayesian inference setting. Because in Bayesian inference, if we want to estimate the posterior distribution, again, our posterior distribution is proportional to the likelihood function times prior. And we have an access to this likelihood function and to this prior in most of the cases. So the only thing we can do is normalize the distribution. And here is the same situation. We again have the access to this energy E of x. So we have an access to our unnormalized probabilistic distribution, and the only thing we can't do is to calculate this Z normalizing constant, because it requires a summation over all possible configuration of spins within the lattice. So it's a sum over 2 in the power of n, where n the number of atoms in our lattice. So it's a huge sum, and we can't calculate it directly. And also because of this, we can't calculate directly all these statistics. So we need to use some approximate methods for Bayesian inference. Okay, let's start with what we already know, with variational inference. So we have a distribution that we can't deal with directly. And in variational inference, we should introduce some more simpler family of distribution where we are going to find the best distribution to the true posterior, to the true distribution P of x. And this time, let's take what is called the mean field approximation. So introduce our family of variational proxy as just a factorized distribution of all atoms in the lattice. So we introduce the property that all atoms in the lattice are actually independent one. And if we consider such family of distributions, we do not need to add here some additional parametric family of each factor qi. It is possible to calculate the best possible qi within this distribution, meaning to minimize the KL divergence with respect to a particular factor qi if we fix all the others. And if we do this, we come to the recalculation formula that is shown here. So each qi is just a discrete distribution with only two values, so it's a Bernoulli distribution, and the probability of that xy is equal to 1 is just can be calculated by this formula, and it uses only the configuration of neighboring atoms within the lattice. So if we know the configuration of all neighboring lattice, we are able to recalculate the probability for the current atom. And then we loop over all the lattice in some order and do it until convergence. And when we come to the optimal variational proxy, we are able to calculate any statistics we want, because now all components are independent. And here you see the graphs, 3 graphs for 3 statistics, the dependence of these statistics with respect to the temperature. And the blue graph are the true answer for this model. And the red graphs are those that we have with variational inference, with the best variational proxy. And the most interesting thing in this third graph, the behavior of our magnetization with respect to the temperature. If we look at the blue graph, we see indeed this phase transition effect. So when temperature is very low, we have a mean magnetization equal to 1, means that we for sure have a magnetic effect within our solid. Then, when we hit our magnet, there is a small interval of temperature, and this magnetization sufficiently drops down. So that is the phase transition effect that we actually want to model, that we observe in practice. However, if you see to the red curve, it also shows some drop of the mean magnetization, but it is shown at a different temperature value. So the critical temperature that is estimated by the red curve is absolutely incorrect. It is not true. And moreover, you may see that the red curve drops down more smoothly, so not so rapid as it done for the blue curve. So if you use variational inference in this model, and you do not have the good approximation for the true distribution P of x, you just get the useless result here, because we can't use the model with the red result. It is incorrect. And the reason for this is our assumption on the that all atoms are independent on each other. Consider these three cases of temperature: the low temperature, the critical temperature where there is the sufficient drop in magnetization, and the high temperature. In the top line, you see the best variational approximation in this case. And for example, in the case of critical temperature, we see that our best variational proxy is almost a random distribution. So for each atom, it is 1/2 that it is 1, and 1/2 that it is -1. And if we see the real sample from the true distribution P of x, we see the picture like this in the bottom. So it is indeed about a half of an atoms that have +1 and about the half of an atoms that have -1. But there for sure has a very strong correlation between each other. So we see that most of the neighboring atoms have the same actually magnetic moment. And it is for sure that we can't model this with the Q of x, which is fully factorized distribution, which doesn't model any correlation between neighboring atoms. And that is why, since our variational proxy is too poor for this model, that is why we have such a bad result and absolutely incorrect estimation of 3 statistics for this model. We could, well, try to invent some maybe more complex variational proxy, but if it is more complex, it could hardly be re-estimated in an efficient way. So the output from this example is that we really need an alternative way to do a Bayesian inference, to estimating the posterior distributions different from variational inference, especially in the case where we really need to do it with a high quality. And our answer to this question is MCMC, Monte Carlo Markov chain methods, which the distinctive features is that they are really able to model exactly the posterior distributions or the distributions that we know only up to a normalizing constant, and to estimate the needed statistics using this. Since there is a Monte Carlo words in the Monte Carlo Markov chain, it means that we're going to address this problem by constructing a sampler from the distribution. So our setting is the following. We have a distribution that we know only up to a normalizing constant. So we have an access to p tilde. And our Monte Carlo method are going to construct samples from this distribution using only access to this p tilde. And if we have a set of samples, we for sure can estimate almost any statistics we want with respect to the distribution by just averaging over this sample the statistics f. So it was a very simple thing. Next, since it is a Markov chain Monte Carlo, it means that we are going to sample the draw samples using some specially construct Markov chain. So the general scheme for constructing the sample is the following. We introduce some transition probability q of x given y, and generate our sample in the following way. So we start from some simple distribution P0. It could be a uniform distribution or standard normal distribution, something that we could easily draw a sample from. So we draw x1 from this P0, and then we draw x2 from our introduced transition probability from q of x given x1, that was generated on the previous time steps, and so on, x3 from q of x given x2, and so on. You may see that this generation mechanism somehow resembles what is going on with normalizing flows. In normalizing flows, we do a similar thing. We start from some simple distribution and then do a set of deterministic transformation to this distribution and finally come to some non-trivial distribution. Here, the sampling mechanism is similar, but the difference is that we do not do a deterministic transformation. Instead, we do a sampling from this transition probability on each time step. And the other difference is that for constructing the sample from the distribution, we just sample only one object for each time step and then collect all the objects for the neighboring time steps as the output of our sampling. As you see, with this generation process, we should do two additional things in order to get really samples from our desired distribution P of x. First, we start from some auxiliary initial distribution P0. It means that our first samples could be really far from the true samples from the distribution. So we start our sampling process, and in practice, we drop out the first, say, 1/3 of a sample that we generate during our generation process. Say that this is a so-called burn-in period of the Markov chain, where we sample not from the true distribution, but from some more from initial distribution. So we need to drop off the first set of samples. And the other thing, since we generate the samples from a Markov chain, it means that the neighboring samples for sure are dependent because they are generated from the transition probability. And if it is okay to use the dependent samples for estimation of some statistics, to average all these samples and estimate in this way. It's okay. But sometimes we really need independent, almost independent samples from the distribution. And again, we can easily get this independent distribution from dependent samples from the samples we have from the Markov chain if we just sparsify our samples and take each tenth, each hundredth of sample, and on the long range, for sure, the neighboring objects will be independent. Okay, and now the main thing is how to construct this transition probability in such a way that our sampling from Markov chain would actually converge to the sampling from our desired distribution, from our posterior distribution. Actually, here there are a lot of different theoretical properties of Markov chain that we may investigate and monitor in order to understand which probability we should use. We are not going to go deep into details with these theoretical properties, and just mention the two main of them. The first property is called the invariant distribution. We should construct our transition probability in such a way that our desired distribution, pi of x, would be the invariant under this Markov chain. What it means? It means that suppose we have already a sample from our true distribution pi of x, and then we transform it using our transition probability. For sure, we should again come to the samples from our desired distribution. If it is not so, we would not be able, in the limit, in the convergence, to sample from our desired distribution. So this is the first property that we should ensure, that our desired distribution is invariant with respect to our transition probability. And the second property is called the ergodicity of the Markov chain. It is about the following thing. We start from some arbitrary distribution P0, and if we denote Pi of x as a distribution taken from our Markov chain at the ith moment of time, we should ensure that if this I goes to infinity, our Pi actually converge to the invariant distribution, to our desired Pi of x. These are two main properties that we need to fulfill to hold for our chosen transition probability. In practice, the first property is usually ensured by the particular sampler. When we introduce some particular sample in the next slide, we can prove that if we construct transition probability in this way, we show that our desired distribution would be invariant under this Markov chain. The second property is more subtle, meaning that in reality we should check for ourselves that in particular case our Markov chain that we construct would indeed be ergodic. This simple criterion for understanding that our particular chain is ergodic is the following property, is that it is possible with non-zero probability with our Markov chain to come from any point to any other point. If this is the true, our Markov chain would be ergodic. So, for example, suppose that our transition probability has the full support, meaning that it is strongly greater than 0 in all our space. It means that there's a non-zero probability to move from any point to any other point. And this is enough to say that our Markov chain would be ergodic. OK. Now let's turn to some particular sampler. We're going to discuss 4 of them. And the first, and I guess the most simple one, is so-called a Gibbs Sampler. It works as follows. Again, we have some distribution that is known only up to normalizing constant. And we need to introduce the transition probability. So we have some point, and how to obtain the next point, how to sample it using the previous one. In Gibbs Sampler, we consider the usually one-dimensional conditionals. So we do not work with a multidimensional distribution that we have to work with, but instead consider all the conditionals of distribution of just one coordinate given all the other fixed. And then we sample the next point by the process that is shown here. So the first coordinate of the new point would be sampling from this conditional distribution of the first coordinate given all the other coordinate fixed from the previous point. Then we use this x1 nu in the next step. So we draw the second coordinate of our new point using, again, this one-dimensional condition, but already with using the previously generated x1 u, and so on, and finally come to the new vector that we output from our sampler. It is possible to prove, it is quite easy, that such procedure would indeed provide an invariance with respect to our desired distribution P of x. Since we move from the multidimensional sampling to sampling from one-dimensional distribution, it is similar to estimation of the one-dimensional integrals. If you need to estimate a one-dimensional integral, you can use just a quadrature formula, and regardless the functions that stays under the integral. It is very easy. The same is true for sampling. If you need to sample from just one-dimensional distribution, regardless the complexity of this distribution, there are methods that could easily do this for arbitrary continuous one-dimensional distribution. So if you are able to calculate this probability, it's not quite difficult to do these one-dimensional samplers. And what about the ergodicity? Again, we can say the sufficient condition that if we suppose that all these conditionals are strictly positive in the whole domain that we work with, it's enough that our Markov chain would be ergodic. So we're able to come from any point to any other point. Okay, okay. Now let's apply this Gibbs sampler to our previous example with easy model, where the variational inference was not very good. So again, we have our desired distribution, and if we want to apply the Gibbs sampling, we should need to consider the conditionals on one variable given all other fixed. And for this particular case, it's easy to derive the exact formula for this distribution. Again, this is a Bernoulli distribution, so very easy to sample from. And we sample distribution using Gibbs sampling scheme and then average. And this blue curve is actually the result of the Gibbs sampler for this model. I've said that this is a true answer, but we know that if we move number of samples to infinity, we would definitely observe the true samples from our distribution. So this blue curve is actually constructed using Gibbs sampler for this case. So very easy. Okay. What about the advantages and disadvantages of this approach? The first thing that should be said is that the Gibbs sampler is an absolutely universal approach. It means that it works both for discrete distributions, for continuous distributions, for mixed distributions. If you are able to calculate the conditional, the next steps are very easy. So it's very general. The next thing, it doesn't have any parameters for tuning. It is also very good because all the other samples that we are going to discuss would have these parameters. And for some of them, this tuning would not be very easy. In Gibbs sampling, we do not have any parameters for tuning. However, if you see the scheme of this method is not, does not work very good if you have a huge dimension case. Suppose you have a bias in neural networks. So you introduce some distribution on all parameters of neural networks. In neural network, you can easily have hundreds of thousands of parameters. And you have this huge multidimensional case. And if you want to apply Gibbs sampler for this case, what you do? You do a conditional sampling. So you have a loop over all this number of parameters in neural networks. Because if you want to sample the second coordinate, for example, you already should know the first coordinate. So this is a consecutive scheme. You can't calculate all the x's in parallel way. And if the dimension is very big, this sampling, just taking one next point, would require a huge number of times. So if your dimension is very big, usually Gibbs sampling cannot be applied. So our next family of samplers would try to solve this problem, meaning that it would try to propose the next point, the next vector, in a parallel way. So it would not loop over coordinates, and in this sense, it could be potentially applied in any dimensional case. This is called the Metropolis sampling, and it works as follows. Again, we have a distribution that we know only up to a normalizing constant, and we introduce some proposal distribution, R of x given y. This could be any distribution we want, some distributions that we could easily draw a sample from. For sure, we can't just draw the samples from this distribution and get the answer. because if it is an arbitrary distribution, our desired distribution would not be invariant with respect to this Markov chain. In order to do our chain invariant, we need to add some rejection step. So our general scheme would be the following. We just sample from our proposal distribution that we choose for ourselves, and then reject or accept some of the points. And we do this with particular formulas. So we calculate this A big, some formula, which requires knowing only unnormalized distribution and our proposal distribution, and then we accept our trial point with a probability proportional to this A. So with probability A, we take our trial point as the next point, and with probability 1 minus A, we choose the previous point as the next point of our sample, meaning we double the point in our sampling scheme, and if we want to then estimate some statistics, we need to count twice this point if our trial were rejected. It is more easy to understand this Metropolis Hastings scheme if we additionally assume that our proposal distribution is symmetric. So if we exchange x and y in proposal distribution, we would have the same value. If this is the case, when we look at our formula for A, we see that this proposal distribution actually cancels from this A, and we come to a more simple formula and for more simple method that is called just Metropolis sampling. And this Metropolis sampling works in a very evident way. So we sample our trial from proposal distribution and then look at the density at the new point. If the density in the new point is higher than the density in the previous point, we accept this point for sure, because we want to traverse through the big values of densities in our feature space. If the density in our trial point is less than the density in the previous point, we again can accept this point, but with a probability proportional to the difference between these two values. So if this probability is too low, we would definitely reject the case. So very simple scheme. So here, one example of applied Metropolis Hastings, just Metropolis scheme. Suppose we want to sample from a two-dimensional correlated distribution with the proposal that is isotropic Gaussian. So so we have the current point. We draw the next point in vicinity of this point from isotropic Gaussian distribution, and then accept it or reject it concerning the formulas for probabilities from Metropolis sampling. So suppose we stay somewhere here. So our green moves correspond to accepting moves, and the red moves correspond to rejection moves. So suppose we stay somewhere here, we draw a point in vicinity of our current point, say go here, and you see that the probability value at this point is much less than probability in the previous point. That is why this point was rejected. In the other case, we go to this direction with the probability that is similar to the probability in the previous point. That is why this point were accepted. And so we traverse in this way through our distribution, and we come to the sampling. However, let's consider the case when this two-dimensional Gaussian distribution has a very constrained set of variables. Suppose it is not like this ellipse, but more elongated one. If this is a more elongated ellipse, as you might imagine, the Metropolis sampling scheme would require you just a huge amount of sampling in order to have a good estimation of your statistics. Why this is so? As you see in our proposal, we are able to move only, with the same probability in all directions in our space.
However, our true distribution is elongated along some diagonal here, so it would be better to move with higher probability to the positive diagonal and with lower probability to the perpendicular dimension. But our proposal distribution doesn't use this information. And because of this, because our proposal distribution do not resemble the true distribution we want to sample from, in this case, the Metropolis scheme, which is show what is called random walk behavior. So we just move in random directions and reject or accept the points. And this for sure, if we go to the other direction, it requires a huge number of steps in order to traverse the area with big value of density. But by the way, the same is true for Gibbs sampling here. Suppose we apply a Gibbs sampler here. So we need to calculate the conditional of one variable given the other variable, and this is easy to do because this is the joint normal distribution, and conditional are also normals with the known parameters. Again, in Gibbs sampler, we do similar like coordinate-wise optimization. So we move in horizontal or vertical direction here, and since our distribution is actually elongated along diagonal, we need a huge number of steps in order to go through this diagonal. So for this case, both the method, Metropolis hastings and Gibbs sampling, will show the very bad behavior, meaning that you have a huge number of samples to generate from it. Okay, and now we come to the third sampler for today, which is called a Hamiltonian Monte Carlo. This is actually a particular case of Metropolis hastings scheme, but with a good proposal distribution. In random walk Metropolis hastings, the problem was that our proposal distribution does not use any information from the desired distribution we want to sample. And this is bad. That is why we have this poor behavior. And in Hamiltonian Monte Carlo, we are going to use the information about the probability that we need to sample from, actually the gradient of this probability, and our method would move to the direction of the gradient, trying to increase the density value. So now let's do a small recap from first course physics in the university about Hamiltonian equations. So suppose we consider the very simple physical setting, like we have one particle that moves in some potential field. For concreteness, let it be some satellite that's moving around a planet. And what we want to do is we want to understand the particular trajectory of this satellite if we move it to the particular height and give it initial velocity and try to understand its trajectory in time. Here we have two kinds of energies, like potential energy and kinetic energy. Potential energy at each position because of the gravity field, and the kinetic energy because of the velocity at each point. And for sure, we can use here just Newton's laws of motion and say that our trajectory should be such that our total energy of the system, the sum of potential and kinetic energy, should preserve at the same level. And actually, the Hamiltonian equation, the Hamiltonian function, is just a sum of this U of x and k of p, the potential and kinetic energy. It's just the equivalent way to write down the second Newton law of motion. It says that our trajectory in time on these two coordinates, on coordinates x and on our momentum, which is proportional to velocity, by their trajectory in time is just described by this first order differential equation. So if we want to understand the trajectory, we just solve this equation starting from some initial conditions and get the result. These are called Hamiltonian equations, and there are many good properties of these Hamiltonian equations. Actually, for today, we need only two of them. The first property which is called Hamiltonian conservation. It shows that if we solve our Hamiltonian dynamics, the value of our Hamiltonian would stay at the same level. So this is just the energy conservation law. And it is very easy to show by just one line of calculation. So we consider the derivative of our Hamiltonian with respect to time, write down it dependence on time, and then put instead of these two derivatives, the result from these equations and come to 0. So the derivative is 0, meaning that the Hamiltonian stays at the constant level. So the Hamiltonian conservation, this is one property, and the other one is so-called reversibility, meaning that if we give some initial conditions at time t for x and p, and solve our Hamiltonian dynamics for some time interval s, so come to the new point x and p at time t plus s, then if we then start our Hamiltonian dynamics from this new point and inverse the time, so go back in time, we would move to the same point that we start initially to this x and p at time t. So this is a one-to-one correspondence if we fix the time interval. Or we can easily check that this is the same as to inverse the momentum at time t plus s and go with the positive time. Again, we come to the same point. Okay, now we would like to use this Hamiltonian dynamics for constructing a good proposal within our Metropolis sampler. So in order to do this, we need to first somehow to introduce the potential energy and kinetic energy into our system. So we have our desired distribution P of x, and what we do, we say that our potential energy is just a minus log of our desired density. So our density corresponds to a potential field in our space. If we now take an arbitrary point, give it 0 velocity, and calculate the Hamiltonian trajectory with this potential field, we would get just an optimization method, because this trajectory would move us to the lowest value of the potential, which corresponds to the mode of the distribution. So very easy. But here we do not need an optimization method. We need a sampler, so we should traverse the area where the density has high value, and this can be easily done if we introduce some momentum, some velocity at each point. So if we introduce some velocity, we would not just collapse to the map, to the mode of the distribution, but we are able to move around it, and if we control this velocity in a good way, we would actually come to the effective sampler. So what we do here, we introduce this joint distribution P dependent on x and auxiliary variable P, which does not have any physical interpretation, and this distribution looks like this. So the first part is just our desired distribution, and the second part, which is just the kinetic energy for this auxiliary momentum variable. And what we like to do, we would like to sample from this joint distribution, sample this x and pi, and if we can do this, we can just drop off the auxiliary momentum variables and take this axis at the output of our sampler. This means that we output the samplers from the marginal distribution on x in this joint distribution, and our marginal distribution on x is just the desired distribution we want to sample from. Okay. So how our proposal would work. So again, Hamiltonian Monte Carlo is just a Metropolis Hastings algorithm with some particular proposal distribution. So we have the previous point, 2 points with 2 coordinates, x and p. And we would like to understand how to produce the next pair of points, x and p. So what we do, first we sample the p from the conditional distribution of p given x old, because this is the best we could do for this P. And because our X and our P in distribution are actually independent, this distribution is just a standard normal distribution with the unit variance. So it's very easy to sample this P from this conditional distribution. Then we have a couple of points, X alt and P, and just solve the Hamiltonian dynamics from starting from this point for some time period. This is one of the parameters of the method that you should choose by yourself. And come to the new couple of points, X nu and P nu, and in this movement, we are guaranteed to conserve our Hamiltonian value. So the Hamiltonian at this pair of points is actually equal to the Hamiltonian at this pair of points. And then, if we use Metropolis Hastings scheme, we need to accept or reject the new point corresponding to the probability A. In this case, we are going to use both properties of the Hamiltonian dynamics that we have discussed, meaning the conservation of Hamiltonian value and the reversibility. The second property, the reversibility, corresponds that we have a symmetric proposal here. So if we go from X alt to X nu, it has the same probability as if we go from X nu back to X alt because of the reversibility property. And that is why our Metropolis Hastings scheme is actually just Metropolis scheme. We do not need this additional Hastings correction. And the other thing, here you see the formula from the Metropolis probability. So we compare just the probability at two couple of points. If we solve our Hamiltonian equation exactly, we are guaranteed to have the same value of the Hamiltonian. And in this case, our new point would be accepted for sure with probability 1. However, in practice, we are solving ordinary differential equation by some numerical methods. And any numerical method has some discretization error. And because of this error, in practice, our real Hamiltonian at new point could differ from the previous one. And in this case, we introduce this rejection probability because otherwise the method would be incorrect. By the way, it's important to know that it's important to sample this velocity, this momentum P at each iteration. If we do not do this, if we just take the previous couple of points and move according to Hamiltonian dynamics, we would not be able to traverse all the distribution. We would move just along the particular level curve of our Hamiltonian. So our Markov chain would not be ergodic. We would not be able to come from any point to any other point. And that is why we need on any iteration to resample this velocity, this momentum variable, and then move using Hamiltonian equation. And actually, the second step is the most important one on why the Hamiltonian Monte Carlo is actually could be much more effective comparing to random walk Metropolis. Because here we could, moving from X alt to X nu, it could be a huge movement in our feature space, and we are guaranteed that with this huge movement, we would preserve the value of our density, which is proportional to the Hamiltonian. That is in contrast to random walk Metropolis, when we do just a small movement from isotropic Gaussian and see whether we can accept or reject the point. Okay, now let's come to the particular solving of our Hamiltonian dynamics and how we are going to use numerical methods. Well, actually, there are a lot of different numerical methods that can be applied for solving ordinary differential equations. I guess many of you can name at least two of them. First, the Euler method, and the second is the Runge-Kutta family of numerical methods. Let's discuss them. So first, start with just the simple possible Euler method, when we just approximate our derivative with the difference derivative and recalculate the x and p using these formulas. So this is the very simple method. The problem is that this is the first order, what is called the first order method, which has a very poor discretization error. So it has a squared, epsilon squared discretization error for one step, meaning discretization error is the difference between the true answer and our numerical answer. And if we do this for time period t big, we would have the total error, which is proportional to the epsilon at the first power. So this is quite inexact method for solving a Hamiltonian equation. There are many other possible variants. For example, we could take a fourth-order Runge-Kutta methods, which is usually the default numerical method for solving ordinary differential equations in most of the libraries. In this case, we for sure would obtain much better result for our Hamiltonian value on the long time horizon. The problem is that this fourth-order Runge-Kutta method would require us a huge number of steps with huge number of calculations on each step in order just to take the next point. It would be the same like a Gibbs sampler for the high-dimensional case. It is too time-consuming. But in reality, we do not need so precise method on each iteration because we do rejection or accepting step after taking the new point. So in practice, people usually use what is called the Leapfrog method, which is shown here. So we first do a half step for the first variable. Then we do the full step for the second variable x using our already new first variable. And then we again do a half step for the first variable. If we do the following, the discretization error would be much better. It is epsilon squared on the horizon of t big. So this method is more concise, and moreover, what is also important, this method is reversible. We know that our Hamiltonian dynamics, if we solve it exactly, would be reversible. But it is not true if we consider a particular numerical method. For example, the Euler method is not reversible, meaning that if you go from the initial point to the answer and then go back, you would come to a different point. And that's why if you want to use an Euler method within the Hamiltonian Monte Carlo, you need to come to Metropolis Hastings correction. And if you use a Leapfrog method, which is guaranteed to be reversible, we do not this Hastings correction. The scheme would again be with symmetric proposal, and we just use this formula for accepting or rejecting the new point. Here, just a simple example of applying the Leapfrog and Euler method for a simple ordinary differential equation. You see that the Euler method indeed increased the error in its solution. And the Leapfrog method, in this particular case, it gives us the exact answer. This is not true in general case, but in general case, for a lot of different Hamiltonians, we can observe the trajectory which is quite similar to the trajectory with the constant Hamiltonian, even for the long time horizon. So using this Leapfrog method is, in practice, usually much better than the Euler one. Okay, and here again our simple example with sampling from the very correlated two-dimensional normal distribution. On the left picture, you see the samples taken from random walk Metropolis. So it is not enough to have all these samples to have a good estimate for the mean of the distribution, for example. And on the right picture, you have actually the same number of samples as in the left, but constructed with a Hamiltonian Monte Carlo. And you see that this method traverses the distribution much better. It covers all the area where the density has high values. And this is because our method goes through the the potential energy that corresponds to our true distribution. So in Hamiltonian Monte Carlo, we would move in this positive diagonal with more probability than in the perpendicular direction. Okay, now just a couple of words about tuning Hamiltonian Monte Carlo method and in general the Metropolis Hastings method. For both this method we have a set of parameters, and a careful tuning of these parameters is actually very important for getting the good sampler. In this seminar, after this lecture, you would play in experiments with tuning your parameters of the sampler. So what parameters do we have? In simple random walk Metropolis sampling, we have a parameter of this variance, so the size of the variance from our proposal distribution. In case of Hamiltonian Monte Carlo, we have two parameters. First, we have this epsilon, discretization step in solving a differential equation. And the other parameter is the number of steps we do, the time horizon. So here we have two parameters, and we need to tune them somehow. And there's a list for some tricks, practical tricks that people usually use when they tune its sampler. So the first thing is that it is usually much better to initialize your sampler with a point with a high density value. So if your density stays somewhere here and you start from this point, it would require you a huge number of steps just to come to the area with the high density points. In some cases, you can provide these points by yourself, but in many other situations, people just use an optimization method. So they start from arbitrary point, go to the mode of the distribution, or to some point close to this mode, and then initialize your sampler from this mode. It would be much better in terms of number of samples you require. The second thing is about the rejection rate. So if you tune the parameters of your sample, you may do some initial sampling and measure the rejection rate you have from your method depending on the parameter. In practice, it is not good to have rejection rates close to 0 or close to 1. If you have rejection rate close to 0, it means that your proposal distribution is too big. You do too big moves, and you do a lot of rejection steps. And so this sampling is inefficient. On the other extreme, if your rejection rate is close to 1, it means that you do very, very tiny steps, which is okay. Most of your points are accepted, but it requires you too many samples in order to traverse the distribution. This is the, yes? In HMC, well, the rejection rate depends on the parameter of your sampler. You could choose the parameter in such a way that your rejection rate would be close to 1 or close to 0 or close to 1/2, for example. And the practical consideration is that you should choose those parameters of your sample in order to have the rejection rate in this interval between 1/4 and 3/4. I want to say that this is similar to the step size in optimization method. In the optimization method, the situation is the same. If you take too small step in the gradient distance, for example, you would reduce your function at any iteration, but it requires you a lot of steps in order to go to the optimum. On the other hand, if you have too big step size in optimization, you would just increase your function, so your method would diverge. And the similar situation is here with the sampler, so you should balance your parameters in order to have rejection rate about 1/2. It would be a good thing. The second thing about the burn-in period, you need to somehow understand how many points you should drop out from the initialization. the simplest possible strategy is just to do the following. You take the budget of the sampler that you may do. For example, you do 10,000 of samples or 100,000 of samples, and just drop out first one-third part of the sampler. Similar to stochastic gradient descent. How many iterations do you need a stochastic gradient descent? You just do it for the time you have. Another possible strategy is to initialize several Markov chains from different initialization to construct a sample, and then to measure the moving average of statistical that you have chosen with respect to these several Markov chains. If all these chains are already in invariant distribution, this moving average would be the same for all the chains. And if they are different, means that the chains didn't mix up. And also one more thing is that you may monitor the autocorrelation function for some scalar, for some coordinate of your samples. So if you, well, in a good case, you should have the autocorrelation function that drops quickly with the lag. So there would be almost no correlation with some interval between the points. And if it is not the case, it means that the correlation between points is high, and you need to tune your parameter somehow. Okay. Now we come to the fourth sampling method, which is called Langevin Monte Carlo, LMC for short. It is again some particular case of Hamiltonian Monte Carlo, which is a particular case of Metropolis Sampler. It works as follows. Suppose we consider just Hamiltonian Monte Carlo with one Leapfrog integration scheme. So integration step. So we would not do many steps, but just one of them. Let's return here. Here you see the formulas for the standard Leapfrog method with half steps for the first variable and the full step for the second variable. Here we may substitute the value for this half step to the formula for our x variable, and the same to substitute this in the last formula. And if we do this, we just eliminate the need to estimate something at the half steps. And we come to the formula that are shown here. So these are corrections for the coordinates and for the velocities. And as for coordinates, you might note that what you do is very similar to just the gradient descent. So what you do with coordinate, you just move, you just do a gradient descent step in trying to lower down the potential energy, meaning trying to increase your density value. So this step would correspond to a gradient descent for potential function, plus you add some noise. Because if you do not add any noise, you just collapse to the mode of distribution. But adding this noise, you will be able to traverse around the mode. And this velocity is somehow controlled by our Hamiltonian dynamics. So if we do many steps, our Leapfrog methods looks like this. And now let's do just one step. If we do just one step, our formula for the x is look like we sample our velocity from a standard normal distribution, and then do a gradient descent step with this additional noise, nothing else. It is written here. So if we consider Hamiltonian Monte Carlo with one step of Leapfrog integration, we have the following calculation. First, sample noise from the standard normal distribution, then do the gradient step with adding this normal distribution, and if we want to apply a rejection, we need to calculate the new value of pi and use it in our formula for rejection probability. However, if you use only one step with quite small epsilon, it means that for sure your Hamiltonian value would not change too much from the previous one. And you may exclude the rejection step at all. You may say that the Hamiltonian at two very close points are quite similar, and this rejection probability would be close to 1. The acceptance probability would be close to 1, and we do not need to calculate this formula and do a rejection or acceptance step. And in this way, the method comes to just the very simple formula that is shown here. So we calculate the next point as a sample from normal distribution with mean calculated by the gradient step with adding some noise. So we do a gradient step plus some noise. That's what we do in Langevin Monte Carlo. From the one hand, it is very good that we do not have any acceptance and rejection probability. But the problem here that in practice, the Langevin Monte Carlo usually works worse than Hamiltonian Monte Carlo. Because in Hamiltonian Monte Carlo, its advantage was to make a huge step in our feature space to traverse along the Hamiltonian dynamics in order to quickly traverse the distribution. But if we do only one step in integration, it is very similar to just a random walk metropolis. For sure, it is not a random walk metropolis because a random walk metropolis corresponds to Euler method, and the Langevin Monte Carlo corresponds to Leapfrog method, and Leapfrog is more accurate with solving the dynamics. But it is only one step. And again, in many cases, you would observe the random walk behavior for this Langevin. However, the main motivation for considering the Langevin Monte Carlo method is stochastic sampling. Now again, let's return to the our simple probabilistic model. We have some prior distribution and the likelihood that the product over all the objects in the training set. For sure, in many cases, we have a huge number of objects in the training set, and we would not like to estimate the full gradient of our probability density and would like to use a stochastic gradient step by using some batches of data. So if we consider a stochastic optimization for finding the mode of posterior distribution, we could just use the following formula. So we just estimate the gradient of the log density by using our batches, by using stochastic gradient. If we solving a variational inference problem, so we optimizing our elbow function. Again, elbow function can be written as a sum over training objects, and that is why in order to optimize it, it is enough to do it in stochastic regime, just to estimate the gradient of an elbow using just a batch of data. But what would we have if we try to apply the Hamiltonian Monte Carlo and use only a batch of data, not the full gradient of our log density? We can say, okay, we have the formulas like this. Here states the full gradient of our log density with respect to x. Let's just change this full gradient to the stochastic gradient. Why not? It would be the approximate estimate, and everything would be okay. However, there is a rejection step in Hamiltonian Monte Carlo, which is written here. The probability of this rejection depends on the full Hamiltonian. So if you want to calculate the true rejection or acceptance probability, here you need to calculate the full Hamiltonian to go through all the objects in your training set. If you estimate this probability using only a batch of data, the method just doesn't work, unfortunately. But this is not the case for Langevin Monte Carlo. As I said, in Langevin Monte Carlo, if we use quite small epsilon, we could do not use a rejection step. We could just make a step and accept the point for sure. And if we do the following sampler, we could just change here the gradient to the stochastic gradient takes small enough epsilon or tend this epsilon to 0 with iterations like it is done in stochastic gradient optimization, and accept every point for sure. And in this case, we would come to the sampler, which to the stochastic sampler that can be applied in stochastic regime, and this means that it can be much more quicker comparing to the full case. And this is actually the main motivation for considering the stochastic Langevin Monte Carlo methods. And the next lecture, the lecture after the seminar after this lecture, would give you much more details on this method, and because this is what is really used in practice now. Okay, now I move to the last point of my lecture. So just let's summarize a bit what we have learned for today. So we have discussed an MCMC algorithm. The main advantage of MCMC algorithm comparing to the variational inference is that the MCMC algorithms are exact if we have number of samples if we tend the number of samples to infinity, finally we come to the true distribution, to the samples from the true distribution. That is why we could estimate our statistics at any tolerance. However, if we compare variational inference and sampling, sampler usually requires much more time, because in sampling you need to do sampling on all the iterations, and each sampling usually requires more time comparing to some deterministic calculation. And in variational inference, you just solve the optimization problem of Albert, so you do not have any sampling, any stochasticity with this within this procedure, so just do deterministic calculation. That is why, in practice, the variational inference usually works much less comparing to the similar sampling method. That is why MCMC method and variational inference method usually combine together. So on the training phase, when you want to learn your the hyperparameter of your model, you optimize the algorithm, so you use variational inference. But on the testing phase, when you already have the learned hyperparameter of the model, and you need on the testing phase to average over the posterior distribution, you apply some sample, sample, in order to get much better estimate for the posterior distribution. Also, it should be noted that many MCMC algorithms have parameters, and it's very important in practice to tune these parameters in a reasonable way. If these parameters are not tuned well, you would not get any good result. But there are almost no procedures, no theoretical things that you can use for tuning these parameters. This is very similar to stochastic gradient descent, when you have choose somehow your learning rate, your batch size, and other things without any particular theoretically guaranteed method. The same is true for MCMC. You should do some practical checks like rejection rate and other things in order to tune everything. And also there are currently some problems with scalability in these MCMC methods. There is a scalable Langevin method, which would be discussed in the next lecture. There is some attempts to construct the stochastic versions of Hamiltonian Monte Carlo methods and some other MCMC methods, but these attempts, I would say, they now require something more, because the algorithms that are derived are not very well justified, and they have additional parameters with very vague argumentation. It's not easy to tune these parameters. So there is some gap in elaborating good scalable MCMC algorithm. Okay, that's all. Thank you. Questions, please? Yes? Could you please repeat in the mic?
So I was just wondering how do gradient-based samplers, such as the Hamiltonian and the Langevin, are dealing with multimodal densities we want to estimate. So if the sampler finds one mode, we'll be able to escape that mode and find the rest of the distribution, or it will just kind of...
Well, in theory, yes. That because we move along the Hamiltonian dynamics, so if the parameters of our proposal are tuned properly, it is possible to sample from multidimensional distributions. You would have the example in the seminar when you sample from bimodal Gaussian distribution, and it is actually possible for Hamiltonian Monte Carlo. And it is not possible for Gibbs Sampler or for random walk Metropolis, which would just collapse to one of the modes.
Okay, thank you.
So could you please reiterate how should I choose the method? So like when should I choose which of these 4 methods in general?
Okay. So if we speak about low-dimensional case, and you are able to apply a Gibbs sampler, and this Gibbs sampler would not show you a random walk behavior, like in this correlated Gaussian example, this is the method of choice, because it doesn't require tuning. It can be applied for discrete variables, because, for example, Hamiltonian Monte Carlo, it uses the gradient of our log density, so it can be applied for discrete variables. If your Gibbs sampler works not very quick because of the dimensionality of the data, because you need to go in a loop through these coordinates, you should choose some Metropolis method, because it proposes the whole new point as a vector. It doesn't loop over the coordinates, and the particular method depends on the situation. So if you are able to apply Hamiltonian Monte Carlo, it is the method of choice, because it could provide a very huge steps in our feature space. So if you do not bother about the stochasticity, if your training set is not very big, you should apply the Hamiltonian Monte Carlo. If you have a big data set, you should use some stochastic sampler, for example, stochastic Langevin or stochastic Hamiltonian. There exist some of them.
Thank you.
Could you please return to tuning HMC and ordinary HMC slide? You write here that acceptance probability should be close to 1 because of
should not be close to 1.
But okay, so the acceptance probability should not be close to 1 because of induced error of a discretization error, or how?
No. Because you do just very small steps. So why your probability is close to 1? You do just very small steps, and that is why your Hamiltonian doesn't change at all, and that's why all the points are accepted. It means that you can make a bigger steps, and your progress would be much higher in this case. This is the same as with the optimization. When you choose the step size for the optimizer, if your steps in optimizer is too small, you would decrease your function at every iteration, but it requires you a huge number of iterations to go to the optimum. You should choose some middle variant in order to, maybe at some iteration you would increase the function, but in most of the case you move to the optimal point. And the same thing is here. If you have some rejection, it is okay. So you do quite big steps in the feature space. Some of them would be rejected, but there would not be too big of them, so you would traverse the distribution in a good way.
Thank you.
So my question is around what exactly is the difference between Langevin Monte Carlo and HMC with one-step leapfrog? So
The difference between Hamiltonian Monte Carlo and which one?
Langevin Monte Carlo. And so on your third last slide, you mentioned that Langevin Monte Carlo is essentially, if we consider HMC with one step in the
Yes.
leapfrog integrator, and then if we have small epsilon, then we can the whatever the second part of the min of one and that thing that will be almost 0. So we will always almost accept the
Yes.
sample that we get. So essentially, Langevin Monte Carlo is like HMC with one-step leapfrog integrator with small epsilon. But then it's interesting because we can sort of scale it to, we can do mini batching. Is that
Yes,
the idea?
yes. This is the main motivation. So if you have a full batch case, you are able to work with full batches. It is much better to use a Hamiltonian Monte Carlo because you are able to do huge steps in your feature space. You do a lot of steps when solve the Hamiltonian equation. But if you have a mini batching, you can't estimate the rejection rate in a good way using mini batches. That is why you need to do these small steps. Langevin Monte Carlo, it works worse than Hamiltonian, but this is the only thing you can do in mini batch case.
Got it. Just one more question. So, and this thing works only when we use small epsilons. If we don't use small epsilon, then we cannot get rid of this accept reject
Yes,
step.
for sure.
Right.
So if epsilon is not small, it could be a case that our Hamiltonian value would be different at a new point and in the old point. And we should account for this in our rejection. Or we should introduce some clever way to estimate this rejection rate using the mini batches. There are also papers that try to introduce such methods.
Thank you.
Thank you for the lecture. I have a question about stochastic case and the HMC. You mentioned that the full likelihood appears in the acceptance rate, and it's not quite clear where does it appear.
So you see here in this formula, here's the state, the Hamiltonian. And the Hamiltonian is the sum of potential energy plus kinetic energy. And the potential energy is just the log density of our, so this is log of P of X, of joint X and theta. So if you want to estimate this value, you need to sum over all the objects.
Okay, thank you.
Are you familiar with any work on MCMC-based autoencoders?
MCMC-based what?
Autoencoders instead of variational autoencoders?
MCMC-based variational autoencoders. You mean using MCMC for within the Elber?
Yes. And whether it's a good idea or not.
Well, actually, this is one of the general approach. If you do not want to use variational inference by some reason, you may, on each step of your optimization, you draw sample using MCMC for the current hyperparameters, and then change them according to the Elba optimization step. However, you see that for all MCMC methods, you have a burn-in period. It means that for every new point, you should draw a lot of samples in order to go to the invariant distribution. So it would be too time inefficient to do this. Or you may use a tiny steps in your optimization, meaning that the neighboring posterior distribution would be similar to each other, and the burn-in period would be okay. Well, there are, well, I guess, 8, 9 years ago, there were some papers that tried this scheme, but all of them appeared to be not efficient comparing to just variational inference approaches.
Thank you.
How do I choose the time interval to simulate a Hamiltonian dynamics for?
Time interval? This is one of the parameters that you should tune.
Any recommendations?
The good thing is that if you fix the epsilon, you may choose the number of steps in a huge interval without any doubt, because you are almost guaranteed that your solver of Hamiltonian dynamics would preserve your Hamiltonian value even on the long horizon. So it's okay just to take 10 or 50 steps. You would approximately conserve the Hamiltonian value. So if you already tuned the epsilon, the normal practice is just to take 10 steps all the time, and it works okay. You may use a 50, but it requires you more computation. So you just take 10 and it works. Okay, thank you. Let's have a break.